webinar. A very good morning to all of you. And I'll just briefly, I understand my presentation is seen now, right?
No,
Okay. So,
ma'am, your presentation is not visible.
not visible. I have put it in slide share mode.
It's
Okay.
not visible to me.
Okay.
Shudita, is it visible to you?
I'll again share my entire screen. Okay.
No, sir, not visible.
Fine. We'll just see. I have shared my entire screen. Now, is it seen?
No, ma'am, nothing is visible.
Because I see that it is sharing your screen. Stop sharing or hide like that. I'm getting. It might take a little while, probably.
Okay, madam. It's okay. It's
It,
bad network quality only.
yeah,
Yes.
but it is seen now. You can see.
Ma'am,
Uh,
Parul,
No.
ma'am, please
Yeah.
turn off your video so that the network problem might
Okay.
be solved.
Maybe. Yeah, I will do that. Okay. I have switched off my video. So now,
yes. Yes,
it,
madam.
it is seen.
It's clear
Great.
now. Yeah.
Great.
Yes,
Okay.
madam. You can start.
Fine.
Thank you.
So we'll today, since your webinar is on wireless, emerging wireless technologies, and how do we connect the future? So today, although my talk is on synthetic aperture radar, polarimetry, my field of work, which is there on polarimetry interferometry, remote sensing of these. So I'll quickly take you to this, and one more component. I just at the end of the thing, if time permits, I'll just briefly outline the quantum experiments that we are doing, quantum communication experiments, since you are all enthusiasts in this emerging wireless technologies. Okay, so the bands which are commonly used for remote sensing in the field of microwave remote sensing in particular, we know that microwave will have right from 1 centimeter to 100 centimeter is the range. So we have P band, which is very high, longer wavelength, which are there, P band, L band, S, C, X. These are C band is very like satellite. Also, a lot of satellite space missions are there in C band also. Then X band, KU band, Ka band. So K, KU, Ka, these are the bands which are typically used for scatterometer. So today we'll be talking about synthetic aperture radar. So let's see, why do we do this micro remote sensing at all? Like all the optical remote sensing or electro-optical region where thermal or in your optical region, when you do remote sensing, it's pretty straightforward, and it's the images are also very easily understandable because it's the way what we see, we observe with our own eyes. Somewhat similar kind of information you get on a synoptic view of the Earth features. But microwave one feature which is there, that is of penetration. So that's why penetration through clouds also it is possible. That's why we have, you are all aware that yes, for communication we use microwaves for that very reason. So when you use it for remote sensing, all weather capability you have, you can have, irrespective, you are eliminating your own source. So during night also you can do it, and if you are doing passive also, you are looking at the emitted energy. So it's a day and night you can image. And then unique sensitivity, all of you are maybe aware that yeah, directed constant of the earth material is the one which significantly affects your backscatter, which is there once you eliminate the target. And as I mentioned, through clouds and then through soil also, and through vegetation, these microwaves are able to penetrate, and you can get information underneath vegetation. You can get underneath the soil. So soil moisture is one of the major applications that you have of micro remote sensing, and the orientation, the structure also you are able to get information, and the roughness of the target. So these are the parameters which you are not able to get when you are typically trying to understand in electro-optical region. As I mentioned, you have, yeah, so, yeah, you can see that the sensor parameters, the wavelength, incidence angle, and the your polarization, they affect your SAR backscatter. And then when you see target parameters, it is a soil moisture, surface roughness, and vegetation canopy broadly. When you are talking about the earth features, the land features. So if you have a very smooth surface, your signal that is incoming signal is there, that's just reflects in the opposite direction, like a mirror like kind of reflection is happening. And if the depending upon the roughness, your coherent component will vary. So coherent and your diffuse component proportion of that will vary, and then accordingly you can get typically if you the SAR sensors are uh, uh, in it has the backscatter is what is being sensed. So if you have a very rough surface, a lot of energy comes back towards your antenna, and that's how you will be able to estimate about the roughness component of it. Similarly, as the moisture increases, the dielectric due to the dipole moment is increases. Due to the dipole moment, the backscatter will increase towards your antenna, because a lot of energy will be radiated. It will your water molecules will try to align itself with the incoming signal, and that's how that due to dipole moment in the same frequency radiation will happen. And as far as the your energy dependence upon the frequency which is there, if you uh, illuminate your target in X band, typically you will be able to interact with just the leaves and the top surface of any canopy, maybe vegetation or forest plantation like that. But if you are at C band, you will be able to go to the twigs and small branches. L band will be able to penetrate right up to the trunk, and it will give you information of the entire structure. And P band would be able to even penetrate after penetrate the entire canopy and the tree trunk and this, and then it will be able to give you the information about the uh, underneath the vegetation also. So that's the
Madam,
typical. Yes.
madam, sorry, sorry to interrupt, madam. Slides are not changing. Have you changed the
Oh,
slides?
oh, it's
We are
not
not
changing
able
at all.
to see.
It's not
No,
changing.
no.
Oh, okay.
Ma'am, even I think that full screen mode also is not visible to us.
Oh,
Only
okay.
the first page is visible to us in browser. Ma'am,
Okay.
is it possible to download that form and you can use some application, Microsoft Word or Microsoft PPT in your system, ma'am? Is it
Okay.
possible?
Can you just see if it is now changing?
No, ma'am, it is not changing, ma'am.
Oh, okay.
Uh,
It's not changing at all.
No,
So
ma'am, no.
I'll open it. That's why I opened with Google Slides also. You want that I should
uh,
just.
Ma'am,
share.
instead of the Google slide, you can do one thing. Please download that PPT, and if in your system there is a Microsoft Word is there, and so then I think it will be okay.
Uh, okay. What I'll do is I'll try to put it in. I'll
Otherwise,
put it
you
in
need to make it
PDF.
full screen mode. You just keep it on the normal mode and change the slide one by one. If
Okay. Now you can just see if it is changing.
no, ma'am, in my system it is not changing, ma'am.
Nothing is changing.
Nothing is
No, only first
changing,
page.
ma'am.
Only the
Only
first
first
slide.
page.
Huh?
Yeah, first slide is visible, madam.
Oh, okay.
You can reshare or otherwise you can take it out and reshare.
I'll close these presentations from here
Yes,
and then
here and
close. I'll open this thing. Okay. Okay. Now you can see this, right? You can see is my screen now seen again, the presentation? Hello?
No, ma'am. I think
Um, Still not seen. Huh? Madam, what I'll do is I have my presentation on my slide in
okay.
a Google link. I'll just share with that link with you. Kindly present it from that side, I think now.
Okay, that you can do, ma'am. Yes, ma'am.
All right?
Ma'am, you can do that, ma'am. You can put the link to this your chat box, or you can mail us, or even you can, ma'am, do one thing in this. You can uh, send us the link to through the WhatsApp also.
Okay.
It's better, madam, if you chat box, if you share directly, it
Okay.
can be opened.
Okay. Yeah, I have put it in the chat box. Kindly, you can.
Suman sir, please share.
Maybe I think that Shudipto can open, ma'am. I think Shudipto can share. Shudipto,
Yes, sir.
please open the link and share from your side.
Okay,
I
sir.
think you
I'm
are
sharing.
you can share, check it, no?
Yes, sir. Yes,
Check
sir.
it that you
I'm doing
can access, you are able to access it or not.
it. Okay, sir. I'm checking.
I also mailed you, ma'am. Susmita Das, ma'am.
Parul ma'am, then you
Yes.
stop sharing, ma'am.
Yeah. Right? I have, right?
Shudipto, is it opening to you in your
Yes, sir. Yes,
system?
sir. Just download the file, sir. I'm sharing my skills, sir.
Okay, you share your screen, please.
Yes, sir.
Great.
Sir, is it visible?
Yes, yes, it is visible. Enable editing. Okay.
Now, sir?
Now it is visible. You just change on a slide. Let us check that it is changing or not.
Yes, sir. Changing. So it is
Okay.
visible,
Okay.
sir. I have changed
Ma'am,
the slide.
yes,
Yes.
yes, it is changing. I think, ma'am, in your screen, is it visible that when we are changing the slide?
Can you just, no, I'm not able to see.
Sudipta, don't show, means end the show.
Okay, sir. Actually, I am unmute myself, sir.
Okay. Ma'am, then you can continue, ma'am.
But no, I don't see the PPT. Maybe I'll leave and then connect again. I'm not sure.
Okay. Ma'am, you can do on the do the thing that you leave and rejoin that meeting again.
Maybe. Yeah, that's what I'll do.
Yes, madam. Please leave and join again.
Okay.
We'll share from our end.
Sudipta? Sudipta?
Yes, sir.
Click on the edit, enable editing.
Enable editing.
Top. On this, just open the PPT.
Okay, sir.
Open the PPT.
Okay. Yes, sir.
Go to the first page, title page.
Yes, sir.
Okay. So now you unmute and make it full screen mode.
Okay, sir.
Some screen one line is coming that.
There you go.
Hello. Yeah, I can
Yes,
see
madam.
now the
Yes.
presentation also. Yeah, fine, great.
Yes.
Okay.
Yes, thank you so
So,
much.
okay, please go to the next slide. Second slide. I was just talking. You are all well aware about the bands which are utilized. Next, please. You can go to the second slide.
Sudipto, please move to the second slide.
Yeah. So these bands, I was just discussing about the bands which are used in that I have already tested. You're all well aware. Okay. Go to the next one. Yes, so whether all I have already described what is the unique sensitivity of micro remote sensing towards the micro remote sensing towards the Earth observations, Earth targets. Next, please. Yes. So this also I was just trying to describe that yes, if you have surface roughness, different types of surface roughness, what is the kind of effect it will have on your SAR backscatter? Whether if it is smooth, it will go away from the your sensor, and if it is rough, depending upon the roughness, the diffuse component will come back towards your antenna, and you will be able to understand what's the surface roughness, or you can retrieve that information. And as the dielectric constant increases, your moisture content increases, dielectric constant also increases, and you get higher backscatter towards your antenna. Your due to the dipole moments, the re-radiation will happen, and the effect of wavelength I was describing, that X band would be able to interact only with the surface, maybe just the leaves, and P band would go right up to the underneath the soil of vegetation also. Next, please. Yes. So the typically, as I mentioned, you have a SAR sensor, you have your antenna, it transmits the signal, and then it interacts with the target, and then you get the return signal back. So you have to take care of the spreading loss which is there, and depending upon the target's characteristics, you will start getting the signal back. So the power that is transmitted, what is the gain of the antenna, and the power that is received. So finally, what you will be getting is you'll be transmitting the power, and then you'll be receiving the power. So you have to take into account all the gain and the spreading loss and the target characteristics. And after all this, you will have to find out that what are the target properties. That's what is finally your goal is. Yeah. Next. Yeah. So typically synthetic aperture radar, what we do is you send the signal from this. This is the beam width I've tried to show here, that when your antenna is of length L, say, then you will have a beam width, your beta into the range of where your target is illuminated. And then that's where you will get the signal from the entire this footprint. But that if your target is in the center of, say, position C, then when your antenna is at position B, this is the first time it will start sensing, and when it is D, that's the last time in the beam width it will see. So you record all the signals, and you can know the phase and the strength, amplitude as well as phase, both of the parameters you record. So you'll know from whether it has traveled thus far, or it has traveled thus far, or it has traveled this length. So later on, once the signal is available to you with all the wavelength, this amplitude and phase, you reconstruct it and synthesize your antenna length to be this big. So in fact, your antenna length will be your footprint of the resolution. Basically, that will be that's the length you can see. You can get that entire. So that is how your resolution is improved in case of synthetic aperture radar. Next, please. Yeah. Next, yeah. So, and polarization, you are all very well aware that you can have linear, either in horizontal or in vertical, or receive also. You can receive your in horizontal as well as vertical, and in circular. So you have a right circular or left circular, or you can have a full right circular transmit and right circular receive, or like that, or you can have hybrid. So that's what we had in RI set 1, from where you had the transmit in circular and receive in horizontal, or and in vertical. So you have a circular transmit and linear receive. So that's the advantage is that you have a very wide footprint you'll be able to cater to. Next. Yeah. So in a typical polarimetry, what happens is, as I mentioned, that you have an incident wave, it interacts with the target, and then you have a scattered wave. So the incident wave is modified based upon the scattering matrix of the target, the scattering in your horizontal and vertical So like and cross polarization combinations you can have, and that's that will tell you about entire scattering property of the target will be known from this scattering matrix, and of course the spreading losses, and this is there. So that's what you get in turn is the received scattered wave. That is what you'll be getting. Next. Yeah. I'll trick, yeah. What is the advantage and why you should have polarimetry? Just that I wanted to tell you once, and then I'll go on to the examples or the actual remote sensing images. So you have if you have a trihedral or dihedral corner reflectors like this, the geometry is totally different for both. But if you look at the backscatter, then your backscattering will be just HH and VV. You will get full, if you transmit in H, 100% will be you'll receive in H, and if you transmit in V, you will get 100% back in V in both the cases. But if you look at the scattering matrix, then for dihedral you'll have 1 0 0 minus 1. So you'll be able to extract the information about the geometry of the dihedral, whereas trihedral you have 1 0 0 1. So from the backscatter signal alone, you do not get this information. But when you have your scattering matrix, you are able to get the information about the structure of the target very accurately. Next, please. And this is for a normal standard target, but you can extend it to any natural targets. Okay, so let's go to this actual real images which are taken at 16 degree, 23 degree, and 47 degree. As you can see in this optical image, the entire red patch is all the vegetation. And in this vegetation, if you look at in a low incidence angle or almost nadir, you'll be able to go towards you'll be able to penetrate through this vegetation and extract information underneath the soil, and which is very well depicted here. Here you can see the moisture content is very high along the canal network, and that's what is very well picked up at 16 degree, because you are able to see underneath soil. And when you go to 23 degree, little bit mix of the vegetation and the soil both is coming. But when you look at 47, the entire energy is interacting only with the crop canopy, and your interaction will be within your entire path length is absorbed within the crop. So what you information you are getting is from the crop. So you can see that this is almost depicting like your optical images of this entire thing, because it's sensing the crop. So if you just change the incidence angle, you can get the information about the canopy as well as underneath soil. So if you take help of both incidence angle, if you illuminate the same target at two locations, you'll be able to get both this. Okay, next please. You may go to the next slide, please. Is a slide, yeah. And here I'm just trying to tell about the effect of wavelength. If you have X band or C band or L band, your penetration depends upon the wavelength. So if you have a longer wavelength, you are able to penetrate underneath the soil. You can see here in X band, there is a canal, there's a river channel which is passing from here near Bhavnagar. This is in the month of April, and we were in the field here, and we could see that there is absolutely no moisture on the surface. So surface was very dry for all the three bands, whether it is X band, C band, or L band. And deep layer, moisture deeper layer, we could find that yes, there is a deeper moisture layer in this patch. You can see very clear this network river channel we can see, but that was meters down. So it was a very with augury. When we had taken the samples, we could see that yes, there is a signal here, and there is a moisture content here, and that could be picked up by L band, but the C band and X band could not pick up at all. So that's the penetration power of the different frequencies. Next. Yeah. And if you take typically paddy crop, it has water as a layer which is beneath the paddy, and you are able to get the signal back from the target and like your paddy crop, and it gets reflected due to the water surface which is there down below, and then there is obstacle of the paddock. So you get basically a double bounce kind of a signal. So that is happening till the time that the entire water body is masked by the vegetation. So till your crop is growing, say 2 months of crop growth is there, till that time you get a double bounce and a very sharp increase with increase of your plant height you will be able to get, and then it gets saturated. So this is typically utilized for delineating paddy. And paddy, you can see that during kharif season, you know that entire area is largely under cloud cover, but still you are able to get very clear cut picture of your rice which is there underneath cloud cover, total cloud cover, and you are able to do a mapping of rice very accurately. But if there is a suppose there is a flood, this also I have tried to show that if there is a flood in between, say in the very initial phase, you are able to map the paddy much before it is harvested. So as early as in August or itself, you come to know that how much area is going to have paddy which is there. But if there is a flood happens in between, then we'll know that okay, how much paddy is affected, how much area is affected by the flood, and what is totally damaged, and what is slightly where the flood has receded and the paddy is still survived. You can see the sky blue color which is here, that shows that in this flooded area down below, I have shown that you can have partially submerged or fully submerged. So only very little area is such that paddy is totally lost. So this is this is Bardhaman district in West Bengal. So you can very accurately map the damage also which is there due to flooding. Next. Yeah, and then plant density also you can actually measure using this multi-polarized signal which is there at C band and L band. You can see that cross polarization. Typically, there is a multiple scattering which is happening under a canopy. So you are able to extract more information because there is a lot of depolarization that is happening. So when you illuminate the target with vertical polarization, and you sense back, you receive the signal in H polarization, you are able to get much higher accuracies. And of course, L band, as I said, will be interacting with the entire structure of your canopy. This is for Prosophis zulifera near Velabadar, Bhavnagar, near Bhavnagar district. So you can see that very accurately your plant per 100 meter, your dense plant density, if you observe, and with the backscatter signal that you are getting, you are very accurately able to measure the plant density. Next, please. Yeah, and okay, next, this I have already shown. Next, you can go to the next one. This is little detail about the flood damage. Next, please. You can go to the yeah, fine. So and if you have a typical settlement, there's a double bounce reflection that is happening. Your incoming signal is there's a mirror like reflection that is happening about that is the interaction that is happening. Then once the wall of a settlement hits is stopping this signal, and then you again get a reflected signal back towards your antenna. So your all the settlements are getting the 100% energy is returning back towards your antenna. So all these bright spots which you see in my top left image, they are all villages near Mathura and Bharatpur area. Bharatpur city you can see down below, and Mathura also. It's all totally in white because the entire energy has come back, and all these small villages are very well picked up. And which, if you try to see, I have compared with the 3 season of optical image, you are not able to pick up these villages or the settlement areas very accurately, because it gets just submerged with the surrounding open areas or which are fallow lands. So you are not able to get that signal. So very digitally you can extract the settlement, human settlement using micro remote sensing. Yeah, next please. Yeah. Now, interferometric coherence is the one which is telling about that if you illuminate the same target with from two different positions with a little baseline in the uh, with two sensors, and then you try to find out that yes, either two antennas on the same your aircraft or same satellite, or two different satellites, and then if you illuminate at the same target with the little baseline change, then you are able to extract the information about the height of the target. And if there is a the coherence is lost, if the very high coherence is there, you are able to find that the target should be steady, so you'll be able to get the information about the height of the target. But if there is a dislocation of the target, if the target is perturbed, then you will not get interferometric coherence, and you will not be able to extract the information about the height of the target. But that can be also utilized in various ways, in particular for flooding and the water bodies. Because you can go to the next one. I'll just show you one water body example that typically on water body. Next, please. In the water body, the surface is typically, if there is a windy, yeah, previous please. Okay. I'm sorry. Yeah, the slide was not changing. Yeah. So you can see in the top left image, there is this dam which is there, and here it appears there's no water, but that is 14th of April, and the very next day there is little water here. But it's not the case that there is no water. All the dark surface, when the signal is hit, it goes in the opposite direction. So so it's all, they are all water body. It acts like a mirror, like a surface. But if there is a wind onto it, then due to the ripples which is there, the signal is returned back towards the antenna. So it appears that there is no water out here, but because of the ripple, there is no coherence between the two interferometric pair of images, and because there is a decorrelation, and typically all the water body, entire water body is never calm, so calm that there is no ripple of any kind. So wherever there is no coherence, coherence is lost. So you are able to delineate this water body very, very accurately, and this is very much useful, particularly when you want to map the flooding. This is in a still kind of a situation I have shown. Here also in the river also it appears that the water has disappeared, but that's not the case. You are able to very accurately measure the water contained water flow of the river. Next, please. Yeah. I've just tried to show the SAR images of this over oceans also, that if there is oil slick, you are able to measure this due to the wind. The oil is accumulated at one place, and you are able to get very accurate information about the oil, because the oil will dampen the surface, and then your surface will appear as a relatively smoother surface onto the wind rough ocean. Ocean typically is having winds, and the water is always disturbed, but the oil will dampen that this, and then you'll get a mirror like reflection, and you're able to extract this information about the oils which are there. Next, please. Yeah, and you can, as I mentioned, for the double bounce for any settlement kind of area, and then when there is water and there is these vessels which are moving, the ship which are moving, you are able to get a double bounce backscatter towards your antenna, and you are very, very, very accurately able to find out about these all the ship movements which are there. You are very accurately able to measure, and it is very much useful for your route, whether it is the routes are followed, or if there are any perturbance which are there, you can inform the ships very accurately. Next, please. Yeah, you can go to the next one, please. Yeah. Okay, this I was just trying to show that yes, if SAR also has a very huge potential using this our own radar imaging satellite. We measured the inaccessible areas of Himalayan glaciers, and we can find out if it is under debris cover, or there's a seasonal frozen snow is there, or wet snow is there, or bare ice zones. So that is the one which tells us about the amount of snow melting which will be there, and how much water will be available, and we are able to map these inaccessible areas very accurately in using this micro remote sensing area, micro remote sensing using, this is C-band, RISET1 C-band multipolarized data is utilized for this purpose. Next, please. You can go to the next slide, please. Yeah. So SAR polarimetry, I'll just now touch upon. I think yeah, a lot of time we have this thing. So we have soil moisture, vegetation, content, surface roughness, and that entire signal which is there, which comes to you, is a combined effect. And SAR polarimetry is able to decompose all these effects and give you information about these parameters. Next, please. Next. Next, please. Yeah. So as I mentioned, you can decompose these targets, and you'll be able to superimpose the different scattering, and then you'll be able to extract different information. Next, I'll just show you some of the examples of this polarimetry. You can move a little, yeah, quickly. You can change the slide, maybe, please. Yeah. So there are various parameters. I'll not go into the details, but I'll just tell that there are different polarimetric parameters that which are sensitive to different target parameters, like surface roughness, or it is dielectric, or whether what kind of distribution whether it's a pure target or a distributed target, or it's a mix of both. So you will be able to find out that, okay, how many scattering mechanisms are there, whether it is just a single bounce or a double bounce, or a volume kind of scattering mechanism. And if there are multiple number of scattering mechanism, because you know that a natural target is not something where only either double bounce will happen or a single bounce will happen, or like that. So you will have multiple scattering mechanisms which is going on. So which one is dominant, whether one is dominant or two scattering mechanisms are dominant, all these informations you are able to extract using SAR polarimetry. Next, please. Next. Hello. You can move to the next one. Yeah, Yamaguchi. So these are all various. Yeah. So this is the scattering mechanism that I was trying to show. That yes, you can from a image. This is a 50 kilometer by 50 kilometer area over Bharatpur near Kevladev Sanctuary is situated here in the center of the image, and you can extract the scattering mechanisms from. You can actually map it, whether you have a double bounce or double reflection or a volume scattering. When you illuminate the target with microwave, what kind of interactions has taken place, and whether it was a pure target or a distributed target. So you will come to know that yes, it is a pure target, then a settlement kind of thing will have just a double bounce kind of signal. So you can see Bharatpur city, and it will very center of the city will tell you about the double bounce. But if you go in the forest areas, then you will see that yes, it will be distributed targets, and you will have volumes scattering that is happening, and depending upon the surface roughness and various conditions, you will be able to extract. Once you have this decomposition has happened about the scattering mechanism which is there, then you can start extracting the information about the surface roughness, or soil moisture content, or the vegetation water content, vegetation volume, vegetation water content. Next, please. Yeah. See, I have just shown that radar vegetation index. So this is telling about you that what is the kind of vegetation which is present. You can see that in during July and August, the vegetation is very little, and gradually, you can see that yes, when the month of November is there, that where the mustard is they start showing the mustard. It's all the vegetation has started increasing, and then after Kharif, like this Kharif is harvested during July, after July and August. So it has all gone into again into the dry. But as the Rabi season starts, the vegetation starts increasing, and once like in January and February, you have mustard and wheat both present. So that vegetation water content, this radar vegetation index is in this region. So a lot of area is vegetated. And in March, you know that typically the wheat is harvested. So everything has gone back to the barren this thing. So the entire vegetation is picked up, and then using this, you can extract the information about the vegetation volume and other things also. So next, I have also shown one example of soil moisture also. Next, please, over this entire year. Yeah, you can see that during July and August, this red is showing drier area, and blue is typically showing the wet. Blue and yellow is the wet. It is showing underneath the vegetation. So all these vegetated area also you can see yellow. So it is very highly moist during the Kharif season, during July and August and September also, because of the rains which are there. And then after September, as you are going to October, most of the area red is showing the drier patches. So it has started growing, showing the dry patches. And again in November, people start irrigating their farms for mustard and preparing for wheat. So in December also you can see that a lot of it has gone from red, it has transited, it is transiting towards green and blue, which is showing higher moisture. And in January and February, a lot of moisture underneath the vegetation it is seen. So this is because we have decomposed the surface and the underneath. So that's how we are able to see the moisture contained underneath the sea and in underneath the crop fields, farmers fields. And in March you can see again it has gone to red. So all the harvesting has taken place. So there is no moisture in the farmers field. So almost every entire area has gone into a very dry patch in month of March. So underneath the crop, you can find the moisture content using this SAR polarimetry. So you are able to get the moisture, you are able to get the vegetation and the roughness also. Next, please. Yeah, and even I've just shown multi-polarized images here. Here it is a P-band image that I have shown. All these pink patches which you are able to see, you do not see that in this L-band image out here. And this water content underneath, moisture content underneath the tall vegetation, which is a thick vegetation, you are able to pick up using this pink, you can see pink patches, which is showing the moisture content in P-band. Which is like almost 1 meter down the crops under in the soil. You are able to pick up the presence of water, which is moisture content, which is there. Next, please. Yeah, I'll just show one example of this polarimetry interferometric SAR. You can see I have shown you here 3 images of C band, L band, and P band. These are all multipolarized images. So HH, HV, and VV you have, and in red, green, and blue. And you can see in this PolInSAR coherence in P band, these patches, these are all Prosophysillifera, Jamun, Kadam, like that. Very tall trees are here in this Keladev sanctuary. Somebody who has visited this, and there is in the center there is wetland. But when you look at these three, this thing in the vegetation, you don't see much difference because it's a very thick vegetation which is present, and very tall trees are which are there. And that if you look at in a coherence, the pollens are coherence, then very accurately you can see the difference between the because underneath the your this your the soil condition are also equal, same soil conditions are there for this entire, because these are all rain fed areas. There is no irrigation or anything which is given, so there is no moisture content wise difference is not there. But because of the coherence, as I said, that due to the movement of the leaves and twigs and this is there, you are able to get the information in PolInSAR coherence, the difference between the type of vegetation. Next, you can just go and one more. Yeah, I have just shown that. Yeah, if you look at the p-band coherence, they and these are all the backscatter only. So if you look at the backscatter, whether it is Prosophis, Jamun or Kadam, there is not much difference. There is hardly a difference of 1 dB or 1.5 dB kind of difference is there in this. But if you look at the PolInSAR coherence, the three Prosophis, Jamun and Kadam, they are so distinctly picked up using this PolInSAR coherence. So that if you have a polarimetric interferometric coherence images, so that is what is going to give you the images very accurately. Next, please. Yeah, please. I'll just touch upon, since you are all from this wireless technologies, I'll just touch upon this quantum frontiers, the experiment that we had done here. Next, please. This is in Prime Minister's stick office. Yes. So quantum frontiers, is very important from quantum mechanics or quantum cryptography, enhanced devices, or free space and fiber based. Both you combine in for quantum cryptography and quantum communication. Your sources, whether it is a single photon or a entangled photon, quantum memories or quantum gates, photonics. These are all the fields in which we are working here at SAC. Next. Yeah, I'll not go into the details how the quantum communication works. You are all well aware that you have a key which is generated, which goes through the quantum channel, and the other information is going through the classical authenticated public channel. Your main signal will go through classical signal, but the key will be distributed in free space using your quantum key will be distributed, and using that key, encryption the data will be encrypted, and you can decrypt and then get the signal. Next, please. I just show the example. Yeah, this is the experiment that we had done in last 19th March in 2021. The first free space end-to-end free space quantum communication over 300 meters we had done. Next. And yeah, so this is the Google image we have tried to show, that almost 300 meters we could achieve using Bob and Alice, and then the signal was transmitted, and we could receive the key, and even video talk was done between the two. Next, please. And this was a single photon, and now then this is an entangled photon also. This February itself we have demonstrated SAC and PRL together. The entangled photon source was developed by PRL, and again the experiment was repeated with this entangled based quantum key distribution over 300 meters, and that's how we could get the successful demonstration using entangled photon source also. Next, please. Yeah, and it was very well appreciated in entire country. Next. So, okay, thank you so much. Thanks a lot for patience hearing. In fact, there was a little glitch. Yeah, okay, thank you. You can post your any questions on my Gmail also. Yeah.
Any questions, please? We'll entertain few questions as time is short.
Good morning, madam. I'm Annapurna from NIT Rourkela. I have one question, ma'am. Ma'am,
Yes.
if in the, am I audible to you, ma'am?
Yes, you are audible. Yes, tell me.
Ma'am, in the quantum-based communication scenario, if quantum QKD-based communication is used, then what about the latency in the communication? Is it being measured through the free space communication?
Well, I'm not expert in this communication, to be very frank, but I can put you in touch with our concerned people. Okay. And you can write to me, and I'll send you across, because this, I just thought that since you're all from communication background, I'll share that this we have very recently this experiment has been done in SAC. Okay. So that
Yes, ma'am.
whether, because that I'll put you in touch with our concerned people. Yes.
Thank you so much, ma'am. Actually, it was a proud to see this type of experiments from ISRO.
Yeah,
Thank you,
that's why I thought I'll just share that, because this entangled also we have done very recently this thing, and we are in fact planning to have one workshop on this, and we'll invite all of you to join, where detailed one full day workshop will be there, where we'll be discussing about this quantum experiments which has happened. So very soon we are planning, we'll be informing Professor Shashmita also, and all of you can join through us. Yes.
Thank you so much, ma'am.
Yeah.
So anyone have any questions?
Thank you so much, madam,
Thank
for
you.
a very valuable presentation, and the recent activities of SAC in quantum communication. It's a very upcoming topic, and we are really hopeful that in the future many people will take it as research
Right.
challenge and solve
Yeah.
it. Okay, the
Yes. Lot of
concerned
research.
teams.
Yeah, a lot of
Yeah.
research is happening in
Yes.
photon source also. In fact, IIT Kharagpur is very actively working. IIT Jodhpur also is working on the
Yes.
atmospheric channels which are there. So that way, the effect of atmosphere onto the quantum communication, because we have to do free space, and
Yes.
right now we are focusing only on optical, like this photonics, but then optical photonics, but we'll be going to microwave photonics also. We are trying to see that microwave radars also, microwave quantum radars. Quantum radar is what is we are working towards. So there this how do you tackle with this? So these are all active areas of research for all the participants. That's why I just thought that yes, it will be of interest, and in our research areas of SAC and our response basket also, a lot of this photonics. In fact, our response basket we have just released 2 days back, I think in 15th of March. Yes.
Yes.
So there, these topics are there, so you can all apply for those topics. And in NIT, of course, there'll be, you can think about more of these advanced R&D. So from that perspective only, I thought I'll just touch upon. Yeah.
Yes, madam. So thank you so much for sparing your valuable time and giving
Okay.
a nice lecture.